Newton rigorously proved Kepler's laws using vector equations in the two-body problem. The velocity moment vector remains constant, meaning motion occurs in one perfectly unchanging plane. Under gravity, a body moves relative to the central mass along a known conic section. Kepler's refined third law allows astronomers to accurately determine the masses of various celestial bodies.
Welcome! Today we're going to embark on a rigorous mathematical journey. Our goal is to derive Kepler's three famous laws of planetary motion, but not from looking at data. Instead, we'll derive them directly from the first principles of Newton's law of universal gravitation. It's a beautiful demonstration of just how powerful Newtonian mechanics really is.
So here's our game plan. We'll proceed in a very logical order. First, we have to establish our mathematical framework. That means getting comfortable with the language of vectors. Then we'll define the classic two-body problem. And from there, we'll derive Kepler's law of areas, figure out the shape of the orbits, and finally, prove the harmony of worlds. You'll see how each law is a direct logical consequence of Newton's theory of gravity.
So let's just start by setting the stage. You have to remember, Johannes Kepler did an immense amount of work. He painstakingly deduced his laws by looking at mountains of observational data. They were empirical. What Isaac Newton did was something different, something much more profound. He established the underlying universal principles, the why, from which Kepler's laws just fall out as a logical consequence. Okay, before we can jump into the physics, we need to get our mathematical toolkit in order. And when you're talking about celestial mechanics, the most elegant and powerful language you can use is the language of vectors. So we're going to define two absolutely crucial operations, the scalar product and the vector product. First up is the scalar product. You probably know it as the dot product. When you take the dot product of two vectors, A and B, you don't get another vector. You get a single number, a scalar. You can think of it as a way of quantifying how much of one vector lies along the direction of the other. It's like asking, what is the length of vector A's shadow on vector B? Now, the vector product, or cross product, this is a completely different beast. It takes two vectors, A and B, and gives you a new vector, C. And this new vector has two very special properties. First, it points in a direction that's perpendicular to the plane that A and B live in. And second, its length, its magnitude, is exactly equal to the area of the little parallelogram that A and B would form. There are two properties of the vector product that are going to be absolutely crucial for our proof. First, the order matters. It's non-commutative. So A cross B is the negative of B cross A. It points in the exact opposite direction. And second, the vector product of any vector with itself is always zero. Which makes sense, right? The angle between them is zero, so the area of the parallelogram they'd form is also zero. All right, with our math toolkit ready, let's finally apply it to the physics. We're going to tackle what's known as the two-body problem. So imagine two masses, think of the sun and a planet, that are only interacting with each other through their mutual gravity, nothing else. And, very importantly, we're watching the system from an inertial frame of reference, basically a non-accelerating viewpoint where Newton's laws hold perfectly. So, let's define their positions. We have two masses, m1 and m2. And we'll use vectors r1 and r2 to mark their locations from some fixed origin. But the really important quantity for us is the relative position vector, r, which is just the vector that points from mass 1 to mass 2. The length of this vector is the distance between them. The derivation itself is a really elegant piece of algebra. We just write down Newton's second law for each of the two bodies. Then we do a clever trick. We subtract one equation from the other. What this does is it lets us get rid of the individual motions and end up with a single beautiful equation that only describes their relative motion. And this is it. This is the fundamental equation for the two-body problem. It tells us that the relative acceleration between the two bodies is directed right along the line connecting them, and its strength depends on the total mass of the system. We've effectively simplified the problem into thinking about a single body moving around a fixed central point. Okay, now that we have this powerful equation, we can start to pull out its consequences. And the first major result we're going to derive is Kepler's second law. We'll do it by showing that a specific quantity related to angular momentum is conserved. It never changes. So how do you find a conserved quantity? Well, in physics, a good trick is to look for things whose rate of change is zero. So let's investigate the rate of change of a very specific vector, the cross product of the relative position, r, and the relative velocity, v. This quantity is the specific angular momentum. Now, when we apply the product rule for differentiation to this, we get two terms. Let's look at the first one. It's the cross product of dr squared dt, which is just the velocity v, with the velocity v. And as we already established from the properties of the vector product, any vector crossed with itself is just zero. So that first term vanishes. Okay, what about the second term? Here we need to substitute in our equation of motion for the acceleration, dv by dt. When we do that, we get the cross product of r with a vector that is also pointing along the direction of r. Because gravity is a central force, the acceleration always points directly along the line connecting the two objects. The two vectors are collinear, so their cross product is also zero. So think about what this means. The time derivative, the rate of change, of our vector rv is 0 plus 0. It's 0. And if the rate of change of something is 0, that something must be a constant. We'll call it c. This vector c never changes, not in its length or its direction. And if its direction is fixed, it means the motion of vectors r and v must be forever confined to a single flat plane. The orbit has to be planar. And here is the final beautiful connection. It turns out that the magnitude of this constant vector c is geometrically equal to twice the rate at which that radius vector r is sweeping out area in space. Since the magnitude of c is constant, the rate of sweeping area must also be constant. And that is precisely Kepler's second law. The line joining a planet and the sun sweeps out equal areas in equal amounts of time. So far, so good. We've proven that the orbit is flat, and we know that the planet's speed changes in a very specific way. But what is the actual geometric shape of that path? To figure that out, we have to actually solve our equation of motion. Now, the integration itself is a bit involved, so we'll just jump to the result. When you solve the equation, this is the answer you get for the trajectory in polar coordinates. And if you've studied geometry, you should recognize this form immediately. This isn't the equation for just one shape. It's the general equation for a whole family of shapes called the conic sections. And this is just fantastic because it tells us that the entire shape of the orbit, whether it's a circle, an ellipse, a parabola, or a hyperbola, is determined by a single number, the eccentricity e. If e is between 0 and 1, you get a closed orbit, an ellipse. But if e is 1 or greater, the object has enough energy to escape forever on a parabolic or hyperbolic path. So what we've really derived is a more complete, a more refined version of Kepler's first law. The orbit isn't just an ellipse, it's one of the conic sections with the central body sitting at one of the focal points. This gives us a complete description of every possible orbit under gravity. All right, we are on the home stretch. We have one more law to prove, Kepler's third law, the beautiful harmonic law. This is the one that connects the size of an orbit to the time it takes to complete one revolution, its period. We're going to derive it by connecting our conserved angular momentum back to the geometry of the ellipse. The strategy here is really clever. We have two different ways of looking at our conserved quantity k. We have an expression for it that comes from the physics, the dynamics of the system, and we have another way of thinking about it from the geometry. It's related to the total area of the ellipse and the orbital period, t. All we have to do is set these two expressions equal to each other, do a little algebraic substitution, and the law just pops out. And here is the result. This is the Newtonian version of Kepler's third law. The cube of the semi-major axis divided by the square of the period is a constant. But look closely. Newton's derivation adds a crucial detail Kepler couldn't have known. The constant depends on the sum of the masses of the two interacting bodies. And so we're done. This final equation is one of the most powerful tools in all of astrophysics. It means that if we can just observe the orbital period and the separation of any two bodies, a moon around a planet around a star, two stars orbiting each other, we can directly calculate the sum of their masses. What started as just a description of how planets move becomes a universal scale for weighing the cosmos. It really makes you wonder what other profound truths are still hidden, just waiting to be derived from our fundamental laws.
Thank you, friends. Strive for understanding and become wiser. See you soon.